better? Okay, all right. So as I was saying today, I think that my main purpose or my main objective is to illustrate how this works so that we feel or the attendants feel comfortable when they use it. And I'm going to try to show that what we're doing is actually extending current workflows beyond the human capabilities. That is, we're going to try to be doing the same thing that we have been doing before, but it's going to be beyond what we can do. Okay. Other thing that we can do with machine learning, or that we have been doing with it, is that it breaks with lengthy, analyst-intensive, model-based processes. That is, we have been doing inversion, trying to get from the seismic information from the well using forward deterministic models, physical models. We have the AVO equations, or the Sopritz equations, the approximations, and we try to make the data fit that particular model so that we can do an inversion and obtain from the seismic, in this case, impedances and probably densities. This is can be very time consuming. You process the data, you do one well and you check the well, you obtain impedances, match it to the well, impedance from the well, it doesn't match, it doesn't tie. You have to go back, you condition the data, and you do that again and again. There was a question before, how difficult is it to incorporate new data? And that talks to this, right? We get a new well, we have to go back, tie that well, it doesn't tie, we have to go back and process the whole data set until we have the optimum that matches everything. So we're trying to break away with that as well, get rid of lengthy, analyst-intensive, model-based processes. We're going to see that its results are easier to interpret and are obtained faster than with conventional workflows. And I think that Robin brought this to bear. He mentioned this. There's still a lot to do. We are just starting to learn how to apply machine learning or to trust it to be used in geosciences. Okay, so this here is this is just what we're trying to do. And what I would like to show here is, here we have seismic, and this is the wavelet, and this is what we're trying to identify. This is lithofacies from well logs, so this is not from the seismic. This, you can see here, this is the seismic wavelet, this is the petrophysical evaluation. We have here in blue dolomite, in yellow we have sand, we have clay in gray, and lime in green. Here we have the fluids, we have porosity and water saturation. Here I put this crossover, indicating the best part of the reservoir. We have here a wet wet leg here of the reservoir. Things to note in here. Previously we had the limit of 1/4 of the wavelet, which means this is, if we consider this a wavelet, we were limited to identifying layers as thick as this. Here we can see that we're identifying in 1/4 of a wavelet, we're actually identifying 2 or 3 different layers. Furthermore, with inversion, what we usually obtain is impedances or rock properties. So we're going to obtain here an impedance, a rock property, or we're going to identify top and base of the sand. Whereas in here, we're actually going to try to assign it lithofacies values. In this case, the wet reservoir, the gas reservoir, the pay reservoir, the wet sand, and then in here we have this layer of clay. And this is what we obtain. Here we are obtaining what is the wet sand. I'm going to talk more about the wet sand in just a minute. We have the pay sand, which is in here as well, and then we have in here the shale. So this is lithofacies from well log, and these are the lithofacies that we're going to be obtaining from the seismic. And we're going to be talking on how we're obtaining this. Now, regarding the water leg, I am considering it, this is still a work in progress. We are considering it more part of these phases. And the reason is that we haven't found a gas-water contact that we can tie to this. If you notice here, if we're talking about the permeable formation, what we would have to see here is a flat spot. So again, We are identifying this as wet sand because that's the well data that we have, but this still needs more work to be done, more information to be incorporated. Going back, you can see here what we had before with the seismic, and you can see the information that we're getting. And again, importantly, is that all this is obtained in about half a wavelength. Now, so that's the same images. Now here, there is another important part of the flow. It integrates two independent data sources. On one side, we have the seismic data, the self-organized maps that Deb and Robin were talking about. On the other side, we have the well data. In this case, we're going to do lithofacies data. And then these two are merged by cross-tabulation. So here, what we're saying is that we're going to compute the sum, we're going to compute the lithofacies, and then we're going to merge them. Notice here that we are not making we're not making the sum times the lithofacies. That is not like the seismic, in which we try to make the seismic, process it such that when we do an inversion, we tie the well. No, we are processing two independent sources, and once they are computed, we are going to compute the lithofacies. Why is this important? When this holds, or I mean, it always holds, when we get a new well, we are not going to have to modify the seismic. We are not going to have to modify the sum. What we're going to do is to do the cross-tabulation. We can evaluate the fit of the well, of that particular well, in the end, using other statistical processes. But again, we don't have to modify the seismic to make a tie. So that's I think, a very important part of this workflow. Now here, the lithofacies log. This should just be lithofacies log. This can be any log. It can be user input. You can create a lithofacies log and then read it in via LAS files. It can be k-means. We can do k-means or Paradise has k-means and cutoffs that can be used to create the lithofacies log. And then we're going to take the sum, and then we're going to do the lithofacies prediction. Okay, another important thing about the self-organized maps, we already mentioned that it's not a process that is dependent on forward modeling, on physical models, is that it is a multi-attribute clustering technique in multi-dimensional space. What does that mean? Let's say that we do an inversion, seismic inversion, and we are so good and we have such a good software that we're going to get exactly the logs at the wells. So this is a log. And again, even in a perfect inversion, let's take a point in here where we have P and S impedances. And you can see that this point here corresponds to both the pay sand and the shale in here. Okay, so there is ambiguity, right? A single point can represent more than one property. Whereas if I add another attribute, in this case density, I can separate very well what is considered the reservoir. So this is what I'm trying to say here is that here I have two attributes, and I'm trying to identify more than two properties, more than two reservoir properties. It is not possible, of course, two attributes and identified. It's like having two equations and three unknowns. I won't be able to identify them. If I start adding more attributes, I am going to be, reducing the uncertainty. So here, still, you can see that for a given point, I still have a more than one value of porosity for the three-dimensional sample. So I can have the same P impedance, S impedance, and density, and I can have more than one porosity value. The same would be for shale or for water saturation or for percent of calcite, percent. So what I'm trying to say is that this can be very ambiguous and non-unique. And the way of reducing that ambiguity or that non-uniqueness is by adding more attributes. But you're going to say, okay, but I'm already looking at 3 dimensions, 3 attributes. How can I bring in more attributes and make the interpretation? And the answer is self-organized maps. That's exactly what self-organized maps do. And before illustrating what I mean by adding the self-organized maps, I would like to I would like to review or make a quick reminder of how the crossplots are done. Here I have two properties, P impedance and S impedance. I am going to take the values at the same depth, and I am going to put them here, right? P and S impedance. This corresponds to this point, and then I'm going to use the color to to color the points of the P and S impedance. We're going to be doing exactly the same with self-organized maps. Okay, this is the same image that Deborah showed a minute ago. And in this case, previously we had three properties. We had P impedance, S impedance, and density, and we created a crossplot. We are going to do exactly the same, but in this case, I am going to be using 8 different properties. So this is going to be an 8-dimensional sample, just like before this was a 3-dimensional sample. So I'm going to take this sample, and I am going to assign it to a cluster. In this case, I'm assigning it to cluster 124. I'm going to go to the next sample. I am going to do the same, assign it to a different cluster, go sample by sample. Here, this cluster resembles this cluster, so I'm going to assign it to this same cluster, or this sample resembles this sample, goes to the same cluster, and keep on going sample by sample. Okay, so what I'm doing here is that I'm going to have 144 clusters in an 8-dimensional space. Okay, so previously we had 3 dimensions right here, 3 dimensions, and we talked about 2 possible clusters, 1 cluster and another cluster. And here I am talking now about having 8 dimensions, 8 attributes, and 144 clusters. Now I'd like to make a brief review here. And another property or another good thing about these methodologies, when we are trying to identify properties using crossplots, let's say that we use this to identify the reservoir, the sand reservoir. We use this, and then we compute other attributes, right? When we are, let's say that I'm now interested in identifying rigidity of the rock or some other property. What I'm going to do is that I'm going to compute more attributes, right? I'm going to compute probably shear impedance or 𝜇 or 𝗣𝗿𝗁, and I am going to do similar crossplots. Now, let's think about it. When we use SUM, we're going to have 10 attributes, maybe 8 attributes, and we don't need to recreate crossplots every time. What we need to do is to create lithofacies logs with the properties that we want to identify, and then tie them to the self-organized maps. So what I'm trying to say is we create a SUM, maybe 10 attributes, and then using the same SUM, we can cross-tabulate with different logs of different lithofacies or different properties that we want to identify, and then compute those properties from the same self-organized map. Okay, so that's what we that's one of the nice things about SUM. Here I am showing the result of using of a SUM, how this looks in the seismic data. Here I have used 7 attributes, created 81 clusters within these 8 attributes, and this is how the seismic data is going to look. Okay, now the other part is that creating the lithofacies log. In this case, we can create it using k-means, and what that does is the k-means is going to take, just like the seismic attributes, the k-means is another clustering technique, the same as the self-organized maps. It's going to cluster data points that fall within a given region in multidimensional space. In this case, I have 4 solids, 2 fluids, and so it's going to have 6 dimensions, and within those 6 dimensions, I am going, or 6 attributes, I'm going to cluster them in multidimensional space, and I am going to show each of the clusters, in this case, in KDEs. So I cluster the data, I take each one of the clusters, and then do KDEs or PDFs of each of the clusters. So this right here is, I created 5 clusters. You can see here, this cluster is lime. This is lime. So this is lime, mostly lime with brine. This thing here is shale and lime. So I'm going to call this shaly lime, and it's wet as well. This is mostly clay. This in here, this is sand. This is quartz, and this is brine. So this is going to be a wet sand. And this in here is sand, and this in here is the water saturation. So this in here is low content of brine, high content of sand. So this is going to be the gas sand. So by clustering in multidimensional space and making an interpretation of the resultant clusters, we can then define the different lithofacies that we're going to be using in our analysis. I take this data, cluster data, I resort it to depth in this case, and I get the lithofacies log. So here, this data sorted results in this log showing the pay sand, the brine. In this case, I don't think we have a shale in this another well. It shows a little shale in here, although we don't have it in here, but we get the lithofacies log. So next step is that, if you remember, we have the lithofacies log here, we have the self-organized maps, and now we are going to cross-tabulate them. What we mean by cross-tabulate, here again I have the same petrophysical evaluation. Here I have the lithofacies log. Here I have the self-organized map. And what I'm going to do is that I'm going to count the samples that match each lithofacies. So let's say lithofacies and neuron. So let's say this is neuron 14, and this is lime. I'm going to count, okay, the first sample. I have neuron 14, lime. Go to the next sample. Neuron 14, lime again. That's 2 times. Neuron 14, lime. And I do the same for every sample. In this case, these are 4 wells that I did this analysis on, and then come up with this table. Now in here, what I'm going to do is that I'm going to go and use the live software. I think it's better to explain with the software here. Okay, so here what we're going to do is we're going to do the first of all, we're taking these 5 petrophysical properties, and we're going to create the KDs. The KD, we're going to do the k-means, and then we're going to plot the KDEs or the PDFs of the different clusters. So that's what I'm showing here. Right here, actually, I created first 8 clusters, and then from the 8 clusters, I reclassified to create the 5 clusters that we are going to be using. So these are 8 clusters that I created, and then reclassified to create the 5 that we're using. And then from here, what I did is, we resorted this to depth to create the lithofacies logs, and we can see the lithofacies logs then. This would be the lithofacies logs. So these are the lithofacies logs. And then the next step, as I mentioned, was to cross-tabulate the lithofacies logs with the self-organized maps right here. And that's where we left the PowerPoint presentation. That's what I'm going to show now. Here we have now the lithofacies. Now here, this image, what we have down in here is the contingency table created by the cross-tabulation. And what it's saying is, okay, if I have neuron 1, in neuron 1, I'm going to have 4 samples of lime, 6 samples of clay lime, 21 samples of clay, 66 of wet sand. And this bar chart shows the same thing. Okay, so neuron 2, I'm going to have 25 samples of lime, 0 of clay, 24, sorry, clay lime, 24 of clay, etc. and it's going to show it in here. Now from here, we make a probability estimation, probability calculation, just a frequentist calculation, in which we take all the samples for a given neuron, or we take a given lithofacies, say lime, and divide it by the sum of all the samples of that particular neuron and compute the probability. So we have in here the probability. And what that probability says is that if I find a neuron 1 and I drill a neuron 1, I'm going to have a probability of 62% of this being a wet sand and a 29% probability of this being a clay. So this again gives you a probability of what you're going to be finding when you identify that neuron and drill on that neuron. Here on this side is the same information. Here we have the the different neurons, and we color this topology map. We color it with the most probable lithofacies. So here we see that the most probable lithofacies of neuron 1 is wet sand with 62%. So I color it blue because blue is the color of wet sand. Neuron 2, the most probable lithofacies is gas sand. So I color it red because it's the pay sand, and so on and so forth. And then, to enhance the interpretation, I change the tone of the neurons. That is, the lighter the color is, the lower the probability. So what you're seeing here is, for example, this is neuron 6. It has a higher probability of being a pay sand than neuron 2. Neuron 2, the highest probability is a pay sand, but this has a 75 probability of being a pay sand, and this has a 32 probability of being a pay sand. So that way, that is how we can, let's say, identify the neurons that are going to have a given highest probability of being a given lithofacies. And down in here, I can just plot the lithofacies and its probability of a given, of a single, single lithofacies. Let's say of pay sand, that would be the probability of pay sand. You can see that also neuron 3 has some probability of having some pay sand, and neuron 7 also has some probability of being a pay sand. And then finally, once that I have this, I am going to save as color map. I'm going to save it. I have it already saved, and I am going to plot it in 3D. Okay, before going to the 3D, I would like to show how can we QC this as well. And what we're seeing here is, in this case, I computed six different topologies, 6 different self-organized maps. And using those 6 self-organized maps, I computed the lithofacies. So here we have one of the wells. This is lithofacies log, and this is the predicted lithofacies from the seismic. So this is a QC that can be done for each one of the wells, and help in the interpretation as well. Now let's go to the seismic. Okay, I'm going to bring the seismic up. Okay, so this is the seismic, and this is the self-organized map with with a default color table. So what we did with the lithofacies is to identify the probabilities of each of the lithofacies and assign color tables, a color table. So now we're going to change the color table to that we created with the lithofacies prediction workflow. I'll take this, and I believe it's this one. Let's see. Yeah, and I think it's this one. And here I can see now. Yeah, I can see now the lithofacies that were computed. Okay, these are false. I created the false, but I'm not showing them here. Jay is going to be talking about the false. Let's see if I can bring the wells. And then I can, I can QC each one of the lithofacies, or in each well. I can compare the lithofacies computed from the seismic to the lithofacies at the wells, computed from the well logs. Okay. So that's very much the workflow that we are using. Any questions up to here? Comments?